Now let us see a very interesting named reaction called Wittig reaction. In fact, it is a property of carbonyl compounds. Of course, the preparation of alkene, very big one, very interesting. Let me consider a carbonyl compound, unsymmetric kind of. Next. Now, when this is treated with something called phosphorus ylide, look at this. We'll give you the full-fledged mechanism, but for now, just see the overall reaction. So this is called phosphorus ylide. See this, interesting. Ylide. Okay. Then obviously we get this alkene R dash double bond C R double dash then R triple dash. Then this. Let me just write it this way. Okay. So this is how alkene can be prepared by Wood's reaction. Okay. Now let me first tell you how the ylides are formed. See, these ylides can be formed by reacting triphenyl phosphine with 1 degree or 2 degree alkyl halides, because it is again a kind of SN2 reaction. Okay, look at this. So this is triphenyl phosphine. Phosphorus belonging to fifth group will have a pair of electron. Okay. This one reacts. Yes. Reacts with something which is unhindered. This is a 2 degree alkyl halide. Okay. Now this 2 degree alkyl halide, of course, is suitable for SN2. Look at this. Triphenyl phosphine is now acting as nucleophile. Attacks the carbon bearing halogen atom from the backside. At the same time, X goes off along with the bonded pair. See, when the lone pair is given to an electron deficient carbon, we consider it as a nucleophile. We call it a nucleophile. Okay. Now check what happens. Okay. Then see what R double dash here, R triple dash here, and there is a hydrogen also. X minus is what is last. Okay, then this one, of course, when treated with a base. Now let me abstract this hydrogen in the form of proton. I mean, without the bonded pair, then this will come here. Of course, we'll take one more step. It actually goes towards this carbon. So that is how we get ylide. Look at this. Okay. So now, let me write the ylide part. C6H5 taken thrice, C plus, because carbon has got the electron pair, C minus, then R double dash, then R triple dash. Hope everything is well and good. Okay, so this is how you get the phosphorus ylide. Okay, now the thing that is eliminated here is B minus has gone out along with the H plus. That is in the form of pH. Right? Check this out. This is how the ylide is formed. We have just done the first part. So ylides are prepared by reacting triphenyl phosphine with a primary or secondary alkyl halide in an SN2 reaction. Okay. And let us go for the mechanism. Very interesting. Be more cautious. Come on. Now let us consider our carbonyl compound. Now this with the ylide. Let me consider this in this format for convenience. This is our ylide. Okay. This is the ylide, right? Now, see the way bonds are formed. Say this negative charge refers to a lone pair. Now, this will attack on the carbonyl carbon as and when it attacks, the bonded pair moves towards oxygen, then this gets a negative charge, and the negative thing attacks on the positive. Always it has to be from the nucleophilic end to the electrophilic end, right? Now, see what we actually get here. RC, very simple but little interesting at the same time. You need to be very careful while writing the things, otherwise it goes wrong. CR double dash, then this is R triple dash, this is oxygen which is connected to phosphorus, and of course there is a bond between these. C6H5 taken thrice. Anything left? Okay, of course oxygen will have this. Yes, all the bonds are okay. Yes, see this of course is called oxaphosphetane. Okay, oxaphosphetane. But you know, when we go for oxaphosphetane, I can actually give you something very interesting that comes in between the ylide and the oxaphosphetane. Look at this R C R dash. You got oxygen with the negative charge. You just keep it as it is, or else, okay, no problem. Then this one, C, you got R double dash, then R triple dash. Okay, I've not attacked the negatively charged oxygen on the positively charged phosphorus. So this is another interesting species called betaine. Betaine intermediate is what I say. Betaine. See the names. Ylide, betaine, then the oxaphosphetane. See, actually now from this, when you show this attack, then it will be this. You get this one. So ylide, then betaine, then oxaphosphetane. Or else if you show the two bonds at a time, straight away oxaphosphetane can be given. But now, see the rearrangement. See, as and when this comes here, we get our alkene. Simple. That's it. So it's just a 3 or 4-step mechanism. R, C, R dash, double bond, C, R double dash, then R triple dash. Along with this, what is the byproduct that we got? This one. Yes, a double bond oxygen. So this is triphenyl phosphine oxide. Okay, that is the byproduct. Okay, now the interesting part is this betaine is dipolar. Okay, has got two poles. The one that has got two poles on its two ends is called a dipole or polar molecule. Okay. Now let me give you an example. Okay. If suppose cyclohexanone is taken plus our ylide. This is our ylide. Then as usual, okay, let us attack it here. This one comes here. We get betaine. Okay. This gets connected to CH2. You've already got oxygen with a negative charge. Then this with a positive charge. So this is our betaine intermediate. Then this attacks and we'll get oxaphosphetane. Okay. This, then CH2, P, C6H5 taken thrice. Yes. Okay. So this is oxaphosphetane. Now this undergoes a simple rearrangement. Take it here, take it here. That's it. You got your alkene. So it's very simple to write the product. Sure. Yes, you got CH2. That's it. Of course, the triphenyl phosphine oxide. Yes. Look at this. It's very easy to write the product when you have the keto or the carbonyl group in the line. You just replace this oxygen by the CH2. Simple. The CH2 gets connected. I mean, whatever is connected to carbon in the ylide, that gets, I mean, that actually replaces the oxygen, you can say. Simple. So that is how the product can be written simply. Okay. Now let us take the last preparation method, that is coal-based electrolysis. We have seen coal-based electrolysis even in alkenes. A similar one. Okay. Now let us consider sodium salt of succinic acid. Okay. So this is sodium succinate. Hope you all know. Oh my such good apple. Okay. Let me tell you what that is. Oh my such good apple. Now look at this. See, these are the dicarboxylic acids. The general formula of the dicarboxylic acids can be given as this. See, this is a dicarboxylic acid. Now if N is equal to 1, that will be ethane dioic acid. So this is ethane dioic acid. Common name is oxalic acid, right? Similarly, when N is equal to 2, it can be given as COOH. No, I'm sorry. I think I'm going wrong. See, when N is equal to 0, it is ethane dioic. When N is equal to 1, it is propane dioic. Look at this. You get a CH2 in between. So N is 1 only, no? See this. N is 1. See, this is, of course, propane dioic acid. Propane dioic acid is also known as malonic acid. So this way, we can give the dicarboxylic acid. So this is oxalic, this is malonic, and now you got a succinic acid here. Succinic is N is 2, right? See, when N is equal to 2, we call it, of course, butane dioic acid or succinic acid. Hope you understand. N is equal to 3. That's pentane dioic acid, nothing but glutaric acid. N is equal to 4. Hexane dioic acid, that is adipic acid. Okay, so this is just for your information. Let us keep it aside. Okay, now take the aqueous solution of sodium succinate when this is subjected to electrolysis. The basic one. We'll have a free radical mechanism. We've already seen this in alkanes. Now, what do we get? CH2 double bond CH2. This, then the CO2. These two are formed at anode. Then you can take this as H plus and OH minus for convenience. But here the mechanism is a free radical kind of 2Na plus then 2OH minus 2NaOH plus H2. These two are formed at cathode. You can make the mechanism, I think. So this is all about coal-based electrolysis. Okay, check. Oh. Now straight away, the properties of alkene. See the characteristic reactions of both alkenes and alkynes. Are electrophilic addition reactions. Okay, electrophilic addition reaction. It is very clear that addition reactions are those in which two molecules add up to give a single molecule. Yes. Then what is electrophilic addition reaction? You know, in electrophilic addition reactions, addition is initiated by an electrophile. Okay. So here the addition starts with the attack of an electrophile. So it's called electrophilic addition reaction. Okay. Now the first electrophilic addition reaction is in fact the addition of hydrogen, but we have already seen that in the preparations of alkanes from alkenes. Isn't it? Alkenes on hydrogenation give alkanes. We have already seen that in the preparations. You can just go through that. Now straight away, let me go for the addition of halogen. Okay, instead of repeating the same, wasting the time, let us go for this. Now the basic reaction is ethylene reacts with bromine, I mean halogen in CCl4 solution. It's very simple. You can actually remember this. You remove a bond. The same thing is what we did in case of hydrogenation. Remove a bond, add a bromine to this, another bromine to this. That's it. It's not the authentic mechanism, but just to uh, actually write the product, we can go with this. Okay. So now we get CH2Br. CH2Br. See, we get 1,2 dibromoethane. 1,2 dibromoethane. Okay. See, this is an interesting reaction in which alkenes and alkynes, that means those with unsaturation, decolorize the orange or red color of bromine in CCl4 solution. Okay. See, in this reaction, alkenes and alkynes, I mean in general the unsaturated ones, unsaturated compounds decolorized the orange or red color of bromine in CCl4 solution. Okay. Only the compounds with unsaturation, not the alkanes. Okay. So this is actually used as a test for unsaturation. It is an identification test. We can detect the presence of unsaturation in a compound taking this reaction into consideration. Okay. Now, let me give you the mechanism.